I'll discuss about modified Milne-Simson method of solving differential equations. So we know that differential equations can describe any system undergoing change. So it can describe all the systems undergoing change. Systems described by differential equations are either complex or the system that they describe are very large, that a purely analytical solution to the equations is not possible. So it is in these complex systems, computer simulations and numerical methods are useful. It is for these complex systems we go for computer simulations and numerical methods. So we know that numerical methods for ordinary differential equations are methods used to find the numerical approximations to the solutions of ordinary differential equations. So first I will discuss about Milne's method of solving first order differential equation with the initial condition. So consider dy by dx equals f of xy with the initial condition y of x naught equals y naught. So integrating both sides between xi minus 3 and xi plus 1, we have yi plus 1 equals yi minus 3 plus integral xi minus 3 to xi plus 1 f of xy dx. So f of xy is approximated by Newton's forward difference interpolation polynomial. So for f of xy, we is replaced by fi minus 3 plus u del fi minus 3 plus u minus 1 by 2 factorial del square fi minus 3 plus u minus 1 u minus 2 by 3 factorial del cube fi minus 3, where u is x minus xi minus 3 by h. So du is same as 1 by h into dx, or dx is h times du. So this integral is rewritten in terms of u. So at x equals xi minus 3, u is 0. At x equals the xi plus 1, u is 4. So yi plus 1 plus equals yi minus 3 plus h times integral u equals 0 to 4 of this expression, that is fi minus 3 plus u del fi minus 3 plus u square minus 1 plus u square minus u by 2 del square fi minus 3 plus u cube minus 3 u square plus 2u by 6 del cube fi minus 3 du. So on integration and using the formula for del fi minus 3 del square fi minus 3 del cube fi minus 3, we have this expression. So this is called as the Milne's predictor formula. So yi plus 1 p is equal to yi minus 3 plus 4h by 3 of 2 times f of xi minus 2 yi minus 2 minus f of xi minus 1 yi minus 1 plus 2 times f of xi yi. So this is the Milne predictor formula. Corrector formula is also derived in a similar way. So in the corrector formula f of xy, for getting the corrector formula f of xy is approximated by the Newton's forward interpolation polynomial, and the differential equation is integrated between xi minus 1 and xi plus 1. So f of xy is replaced by this forward interpolation polynomial fi minus 1 plus u del fi minus 1 plus u into u minus 1 by 2 factorial del square fi minus 1. So where u is x minus xi minus 1 by h. So here dx is h times du. So when x takes a lower limit, u is 0. When x takes the upper limit xi plus 1, u is 2. So yi minus 1 plus h times integral 0 to 2 fi minus 1 plus u del fi minus 1 plus u square minus u by 2 del square fi minus 1 du. So on integration and then substituting for del and del square, we get this expression. So this is called as the Milne's corrector formula. So this is denoted by I plus 1c I plus 1c. So if the difference between the predictor and value and corrector value is not small, we use this formula again. So this is the first approximation of the corrector formula. If the difference is not small, we use this formula for the second time. When we use it for the second time, yi plus 1p is replaced by yi plus 1 c1. The first approximation is denoted by y. I plus 1 C1. To get the second approximation, y I plus 1 P is replaced by y I plus 1 C1. So we proceed in the same way till the difference between the predictor and corrector value is small. Now I will explain about the modified Milne's Simson method of solving delayed differential equations. So we know that ordinary differential equations play an important role in science and engineering. Delayed differential equations are a type of differential equations in which the derivatives of the unknown function at a certain time is given in terms of values of the function at previous times. So delayed differential equations are a type of differential equations in which the derivatives of the unknown function at a certain time is expressed in terms of values of the function at previous times. So delayed differential equations, in short DDE, they occur in the class of dynamical system. They frequently occur in the class of dynamical systems. They have applications in they arise in population dynamics, electrodynamics, communication networks, physiology, and chemical kinetics. Analytical solution of delayed differential equations are not as easy compared to analytical solution of ordinary differential equations. Analytical solution of delayed differential equations are difficult than analytical solution of ordinary differential equations. Numerical techniques play a crucial role in finding the solution of DDEs. So during the past 30 years, the numerical solutions of DDEs are based on the extension or the modification of the traditional numerical methods of solving ODEs, like modified power series method, the pseudo RK method, Legendre Gauss collocation method, and so on. So the numerical solutions of DDEs are based on during the past 20 years or 30 years, the numerical solutions of DDEs were based on the extension or modification of the traditional numerical methods like modified power series method, fourth order pseudo RK method, Legendre Gauss collocation method, and so on. So now we will see the solution of delayed differential equation. So consider the initial value problem for delayed differential equations. So y dash of t is equal to f of t, y of t, y of t minus tau. Y dash of t is f of t, y of t, y of t minus tau, y of t equals pi of t, where tau less than or equal to t less than or equal to 0. So this is the IVP of delayed differential equation. Tau is called as the delay or lags, which is always non-negative. The delay tau may be just constant. It is the constant delay case, or a function of t, tau equals tau of t, the time dependent delay case, or tau equals tau of t, y of t, the state dependent delay case. So the term y of t minus tau is called as the delay term. The term y of t minus tau is called as the delay term, and the approximation of the delay term is denoted by v. So integrating this equation between integrating this differential equation between t1 and tn plus 1, we have integrating the differential equation from tn to tn plus 1 on both sides. We have yn plus 1 equals yn plus integral tn to tn plus 1 f of t, y of t, y of t minus tau dt. Now we will see Milne-Simson method of solving the IVP for DDEs, that is a delayed differential equations. The predictor corrector formulae are given by yn plus 1 p equals yn minus 3 plus 4h by 3 of 2fn minus fn minus 1 plus 2 fn minus 2, and the corrector formula is yn plus 1 c equals yn minus 1 plus h by 3 of fn plus 1 p minus 4 fn plus fn minus 1. So this is called as the Milne Simson predictor corrector method for the delayed these two are used for delayed differential equations. Now we describe a new method introduced by Dr.K and Jaffrey. It is called as in short it is DJM, Dr.K and Jaffrey method. It is in short it is DJM for solving linear and non-linear functional equation of the form u equals f plus n of u, where f is a known function, n is a non-linear operator. So we assume that the solution takes up the series form. So here we assume that the solution takes up the series form. So we take up linear and non-linear functional equation of the form u equals f plus n of u. F is a known function, n is a non-linear operator. We assume that the solution is in the form of a series, that is u equals summation I equals 0 to infinity ui. The non-linear operator n is decomposed by DJM as follows. So n of u is n of this summation. The summation is split as n of u naught plus summation 1 to infinity. See, the summation is split as n of u naught, that is a first term, plus summation I equals 1 to infinity into the sum of the terms from u naught to ui, that is you will have I plus 1 terms, and minus the sum of the terms from u naught to ui minus 1. So this difference will give you ui. So see n of u is n of summation ui. It is split as n of u naught plus summation I equals 1 to infinity n of the summation uj j equals 0 to I, that is sum of the terms from u naught to ui minus n of the sum of the terms from u naught to ui minus 1. So sum of I plus 1 terms, here you will have I plus 1 terms minus sum of I terms. So this expression is taken as gi. This whole expression is taken as gi. So summation I equals 0 to infinity gi. So where g naught equals n of u naught, the initial value, gi is this this expression, that is n of summation uj j equals 0 to I minus n of summation uj j equals 0 to I minus 1 for I greater than or equal to 1. Now, so from equations 3.2 and 3.3, from these two equations, the first one u equals f plus n of u can be, in place of u we have ui, and in place of u we have ui, u is replaced by ui, u equals f plus n of u. In place of u equals f plus n of u, you have ui, that is summation I equals 0 to infinity ui equals f plus summation n of u is taken as summation gi, n of u is taken as summation gi. See ui, so in place of u you have summation ui, in place of u you have summation ui equals f plus, in place of n of u you have summation gi. So so this is the expression we have from the equations 3.2 and 3.3. So now we define the DJM series terms as follows. U naught is f, u1 is n of u naught, u naught is taken as f, u1 is n of u naught, um plus 1 is n of u naught to um, n of the u naught plus u1 plus etc. um minus n of u naught plus u1 plus etc. um minus 1, where m equals 1 to etc. So n of sum of m plus 1 terms minus n of the sum of m terms. So the kth approximate solution is given by u equals summation I equals 0 to k minus 1 of ui. So the DJM series solution is expressed as follows. U naught equals F, U1 equals N of U naught, Um plus 1 equals N of U1, U naught plus U1 etc. Um minus N of U naught plus U1 etc. Um minus 1. So the kth approximate solution is given by U equals summation I equals 0 to k minus 1 Ui for suitable integer k. Now we will get into modified Milne-Simson method. So this method was given by DJM. This method was given by DJ, that is the above method was given by Daftader and Jaffrey. So the method is named after them. It is called as Daftader and Jaffrey method. Now we will get into modified Milne-Simson method. So we have modification of Milne-Simson method by employing DJM. The value of the definite integral on right side of the equation 2.2. So what is 2.2? It is the solution of the delayed differential equation. We have the IVP of delayed differential equation whose solution is yn plus 1 equals yn plus integral Tn to Tn plus 1 f of t, y of t minus tau. So here we have modification of Milne-Simson method by employing DJM. So the value of definite integral in the equation 2.2. So this equation is modified by, this equation is the value of the definite integral in equation 2.2 is approximated by Milne-Simson implicit method as yn plus 1 equals yn minus 1 plus h by 3 of f of tn plus 1 yn plus 1 vn plus 1 plus 4 times f of tn yn vn plus f of tn minus 1 yn minus 1 vn minus 1, where n varies from 3 to m minus 1 and h is the difference Tn plus 1 minus Tn. Tn equals T naught plus Nh. So we have the equation U equals F plus N of U as, so this is the solution given by DJM. So U is taken as yn plus 1. F equals, this is a predictor value, F equals yn plus 1 p. So that is same as yn plus 1 plus 4h by 3 plus 4h by 3 of f of tn yn vn plus h by 3 of f of tn minus 1 yn minus 1 vn minus 1, and n of u is this term h by 3 f of tn plus 1 yn plus 1 vn plus 1. I repeat, 4 point, this equation is expressed in the form u equals f plus n of u, where u is yn plus 1 and f is yn plus 1 p. The predictor value is given by yn minus 1 plus the second term, that is 4h by 3 f of tn yn vn plus the last term h by 3 of f of tn minus 1 yn minus 1 vn minus 1, and n of u is this term, that is h by 3 f of tn plus 1 yn plus 1 vn plus 1. So now we use DJM to get the 4-term solution. So what is the kth term approximate solution? That is summation ui I equals 0 to k minus 1. So kth term approximate solution is given by summation I varying from 0 to k minus 1 ui. So for the fourth solution, for the fourth term solution, you will have summation I equals 0 to 4 minus 1, that is 3. So if k is 4, you will have summation I equals 0 to 3 ui. So u equals u naught plus u1 plus u2 plus u3. U naught, what is u1? u1 is n of u naught. u1 is n of u naught, and for u2 we use this formula. So if m is 1, you will have u2 as n of u naught plus u1 minus n of u naught. So for u2 you have n of u naught plus u1 minus n of u naught. For u3 you take m as 2 here, u3 you will get it as n of u naught plus u1 plus u2 minus n of u naught plus u1. So I repeat, u naught is written as such. U1 is same as n of u naught. U2 is written by taking m as 1 here. If m is to 1, u2 you will have u2 as n of u naught plus u1 minus n of u naught. If m is 2, you will have u3 as n of u naught plus u1 plus u2 minus n of u naught plus u1. Then so in this, n of u naught gets cancelled, n of u naught plus u1 also gets cancelled. So you have u naught plus n of u naught plus u1 plus u2. I repeat, n of u naught gets cancelled and n of u naught plus u1 also gets cancelled. So you are left with u naught plus n of u naught plus u1 plus u2. So n of u naught, what is u1? N of u naught. What is u2? u2 is same as n of u naught plus u1 minus n of u naught. That's what you have here. So that is u naught plus n of. So here again within the brackets n of u naught gets cancelled. So n of u naught plus n of u naught, and this u1 is replaced by n of u naught. So we have u as u naught plus n of u naught plus n of u naught plus n of u naught. So what is u? yn plus 1. So yn plus 1c, that is a character value. Yn plus 1c, u naught is a predictor value, that is yn plus 1p plus n of u naught, that is yn plus 1p plus n of u naught is replaced by yn plus 1p in every term. So that's what you have here. See, I repeat, u is the character value yn plus 1c, u naught is a predictor value yn plus 1p. So in place of u naught you have yn plus p everywhere. Then in the next step you have what is n of u? H by 3 of f of tn plus 1, yn plus 1, vn plus 1. So n of this term is replaced by this. N of this term is replaced by h by 3 of f of this form, tn plus 1, yn plus 1, vn plus 1. What is n of u? H by 3 f of tn plus 1, yn plus 1, vn plus 1. So n of this bracket term is replaced by h by 3. So for the outer n you have h by 3 f of this. Again for the inner n you have h by 3 of f of tn plus 1, yn plus 1p, vn plus 1. So this is the character formula. This is a modified Milne Simson character formula, and this is the modified Milne predictor formula. So so this is the modified Milne Simson method of the solution of the delayed differential equations. Now to get this can be reduced to modified Milne Simson method of solving ordinary differential equations. Whatever we have got is for the delayed differential equations. So if you take Vn as 0, you will get the modified Milne Simson method solution of ordinary differential equations. So if Vn is 0, you will have if Vn is 0, you will have the solution as, if Vn is 0, you will have the you will have the differential equation y dash equals f of t y of t, y of 0 equals y naught. The following modified Milne Simson method by applying 4-term so we have seen the modified Milne Simson solution of delayed differential equations. From the modified Milne Simson solution of delayed differential equations, we can get the solution for ordinary differential equations by taking the approximation of the delay term as 0. So the delay term in delayed differential equation is y of t minus tau. So this the term y of t minus tau is called as the delay term. If the approximation of the delay term is taken as 0, the approximation of this delay term is Vn. If Vn is taken as 0, then we have the IVP as y dash equals y of t y dash equals f of t y of t. If the approximation of the delay term is taken as 0, that is Vn is taken as 0 in the delay differential equations, you have y dash as f of t y of t with y of 0 equals y naught. If Vn is taken as 0 in both predictor and corrector formula of the delay differential equations, you will get the predictor and corrector formula for the ordinary differential equations. So I have discussed the paper Modified Milne-Simson Method of Solving Differential Equations. In the paper, the authors have applied DJM on implicit Milne-Simson method to derive the proposed method. The authors have used implicit Milne-Simson method to derive the modified Milne-Simson method. The efficiency of this method is tested on various types of problems, and it was found that this method gives better solution compared to other methods, and the solutions are also close to the exact solutions. So I will upload this paper in the department GCR. You all can go through the paper for a better understanding of the work done by the authors. Thank you.